Okay. Does it work? Yes, I think so. Okay, I'll start. So I'll start by introducing myself. I will be the chairman of my session. My name is Oliviero Andreussi. I am a senior postdoc at EPFL and Università della Svizzera Italiana. I work with Nicola Marzari, and you'll see more people from his group presenting you the AIDA technology, and maybe you have seen other people that worked with Nicola Marzari in the past days. And so now I'm starting from the assumption that you are all very familiar with Quantum Espresso and all the simulations that you can perform with the package and with like plane waves, pseudopotentials, and everything. So we'll look at something slightly orthogonal, which is solvation and environment effects. And in particular, we'll speak about continuum models and their implementation in what is called the Environ plugin, which is not currently distributed together with Quantum Espresso, but is part of the Quantum Espresso family. It is hosted in the QForge website. I will present you some of the details of the module. Continuum models are more traditional of quantum chemistry. I don't know the background you come from. I guess most of you are more in the condensed matter physics. And so I'll try to convince you that they can actually be useful also in condensed matter. So this is the outline of my lecture. I will, as I said, give you some motivations to use this kind of multi-scale approach, and show you a brief history of continuum models of observation, especially regarding the quantum chemistry origin. And then I will speak about the model that we developed together with Nicola Marzari and other collaborators, which we call the self-consistent continuum solvation. And it contains different contributions, so it's a rather, there are different kind of environment embeddings involved in this model. And then, as I said, I will speak about the implementation of this model, so the Environ library, and how it couples with the different programs of Quantum Espresso. So to give you an idea of the motivation, let's look at like a work that may appear in the literature about like discovering new materials. So this is, for example, one example regarding catalyst for fuel cells or metal air batteries. And so, our task as scientists or material scientists in condensed matter is usually the one to figure out the revolutionary material that will change and solve the problems of the world. And one way would be, for example, to devise an electrode material which allows to do, for example, the oxygen reduction reaction, which is one of the key steps in fuel cells, and doesn't require, it's not as expensive as the traditional electrodes, which are usually made of platinum, and is maybe even more efficient in doing this reaction. So, what do you need as to perform simulations on this kind of materials? So what would be your approach if you want to study, the next cathode materials for fuel cells? So do you have, by the way, feel free to interrupt me, to ask questions. If something is not clear, I'm more than happy to repeat things over and over. I think I have less slides than the ones I'm used to do for the amount of time that I'm allowed to speak. So, we have some time to go into the details. And so, okay, so let's say that you want to study like perovskite oxides to see how they work as a catalyst for the oxygen reduction reaction. So how would you set up like your activity, your research activity? What would you compute? What kind of systems? What kind of properties? Do you have an idea? What would be your first, let's say, thoughts when you look at an article from like this? So the first thought that I would have is, them, these are experimental work. Why hasn't some computational scientist figured out the same materials before the experiment did it? So the first thing that we should aim as computational scientists would be, we should really be the one doing the predictive work. We should really be the ones proposing new materials. Why every time we should wait for the experimentalists to figure out a new class of materials, and then instead we have to figure out why these materials work and maybe try to see if in the same class of materials we can do a bit better or find a slightly better material. So the first thing that comes to my mind is why the hell are the experimentalists always first and we can't be first? I hope there are not many experimentalists among you. And the second thing that I would think is how can I set up a calculation that can give me access to a property related to the catalytic activity and I mean, for example, maybe I can have a look at the band structure of these materials. I can set up a simulation cell, like a minimal simulation cell for these materials, which are in the perovskite structure. I can perform a DFT calculation, and I can compute the band structure and look at the maybe HOMO-LUMO position of the bands, and see if these are, compared to the standard hydrogen electrode, if the potential of these bands are in the right region to perform water oxidation or water reduction. So oxygen oxidation, oxygen reduction or oxidation. And so I can set up, for example, a DFT calculation of band structure of a perovskite. But then my question would be, is this calculation accurate enough? Can I use DFT? Which flavor of DFT? And then I can ask myself, is the band structure enough to predict the catalytic activity, or do I need to perform like more advanced calculation? Maybe I should really look at the catalytic reaction. So I have oxygen on a surface of the catalyst and look at what happened to O2 when it adsorbs and maybe dissociate and then form water on top of the surface. So maybe I should switch from a bulk calculation to a surface calculation. And in that case, I also have many concerns. I will also have many concerns regarding the accuracy of my calculation. I mean, how many layers of the material should I simulate to have a realistic surface? How much vacuum should I put in my simulation cell to avoid the interaction between replicas and things like this? So, as I said, we can do bulk calculations. Then maybe I can do a large elastic band calculation. So I can, I'm not sure it was covered in the topics, but okay. So you can perform a calculation looking for transition states or reaction pathways between two different structures. And, or I can run molecular dynamics simulations and then let the system evolve and look at what happens with the system and maybe a biased molecular dynamics using metadynamics or some biasing technique. And so these are all possible calculations that I can perform on my system. Clearly, the more complicated the calculation, the more, ideally, the more I will learn about the reactions and the more I will be able to exploit my simulations to predict, to come close to what experimentally they see all about the catalytic activity of the system. But I mean, as I increase the complexity of the calculation involved, I also have to increase the complexity of the system that I want to simulate. I mean, if I go from bulk to surface, my system will become much more complicated in terms of number of atoms and simulation cell. And then eventually, if I want to study catalytic activity of an electrode in an electrochemical fuel cell, I also have to take into account of all the rest. I mean, the surface and the reacting species are not alone in vacuum in a real experimental setup. I should also consider the fact that this is in the presence of a liquid solution, the electrolyte. Then there is maybe an applied electrochemical potential to the system, so I have maybe some counter ions in the electrolyte, which form form a diffuse layer, an electrochemical diffuse layer in my system, and allows the presence of a finite electric field in my simulation cell. And then I may be interested in looking at defects, because maybe this reaction doesn't happen on the ideal flat surface. Maybe it happens on steps or like defects on the surface. And as I want to be more and more predictive with my calculations, I'm required to have to go towards more accurate calculations. So maybe DFT is not enough. Maybe I need to perform GW calculations. But I also need to go towards more complex simulations. So I need to include more and more ingredients in my cell in order for it to be like realistic, to be close to what experimentally is seen. And these two problems are the main problems that still hinder the capabilities of computational science in arriving first in predicting new materials. So this is why most of the times experimentalists give your first input, and then maybe you try to figure out why this works, how can I simplify the experimental system. So there should be a way to include the complexity of this kind of environments in first principle simulations without increasing too much the computational cost of your simulation, and that still allowing to do high throughput calculations, so to repeat the calculations for several different conditions, several different setups, maybe using different molecules, or defects, or different electrolytes, different surfaces. So how far can we go with full atomistic quantum mechanical simulations in this direction? So clearly, I mean, if you want to simulate, this is, for example, a surface with some electrochemical species, which are the blue dots, and then water solution on top of it. So if you want to do this fully atomistically, then you should ask yourself how large the simulation cell should be. Do you have any idea of how big should be a simulation to perform a reasonable calculation for this kind of setup? Angstroms, see, but I mean, 1 angstrom, 2 angstrom, or? Yeah, so at least tens of angstroms. And this is due to the fact, clearly, I mean, it's related to the surface. If you want to have, I mean, if you are an absorbed species on a surface and you don't want to have a very high concentration of absorbed species, you need to have like a supercell of the surface so that like one absorbed species doesn't see the others which are in the periodic images. And so let's say the lateral dimension, is clearly related to the features that you have on the surface. So maybe if you want to introduce steps or defects on the surface, then you may need to consider a larger supercell. But the orthogonal direction is controlled by how much of the electrolyte solution you want to simulate. And well, if you have a system with like no counter ions, no electric field, maybe you want to have like a few angstrom on this direction so that you have a reasonably enough liquid on top of the system. But let's say that you have an applied electrochemical, you have a charged slab, and then you have some electrolytes, some salts in the liquid. So like the typical length scales of the diffuse layer, which is the distribution of counter ions in an electrochemical system, is of the order of nanometers if you have a not very high counter ion concentration. So if you really want to have all the ingredients in place, then you would really need a huge simulation cell to include all the water, I mean, all the counter ions effects, all the water molecules. And then also water, I mean, is a liquid. So maybe you are happy enough with simulating water with 32 molecules, but then you may wonder if 32 water molecules really sample configurations which we call liquid configurations, in the sense that the system is small, you have periodicity artifacts, and are these water molecules really liquid? So how many water molecules? It's also important because every water molecule has how many electrons? wild guess? 6, 8, 10? 10, okay. And, well, 10 if you consider all electrons. If you have pseudo potentials, 6 plus 2, 8. Right. And, but let's say 10. I mean, it's just an order of magnitude estimate. So why are these two factors important? Why is the simulation, the size of the simulation cell and the number of electrons important? But by now you should know that the cost of a quantum espresso calculation, a PW calculation, a CP calculation, or I mean more advanced calculations, scale with the system, the cell size, because the number of plane waves that you have to include in your basis set, giving a certain accuracy that we want to fix, scale as the size of the cell. The larger the cell, the more plane waves you need to include in your basis set. Because this you should have seen already in the slides, I mean, in the presentations before. But the real bottleneck is related to the number of electrons, because a density functional theory calculation scales cubically with the number of electrons. So if maybe you can simulate a system with a few water molecules, if you have to include 100 water molecules, then you have 1,000 more electrons, and the system is 1,000 at the cube power more slower than a simulation in which you would just have no water molecules at all. So clearly, I mean, it's very important to, I mean, it's possible to do fully atomistic simulations with some of these, I mean, on a snapshots like this. The real problem is that when you have something which is liquid or amorphous, it's not just a question of performing a single DFT calculation of the whole cell. You also need to sample the configurations of the liquid or the amorphous, because those are disordered configurations. And the property that you look at is not just the property of the single snapshot, it's an ensemble average of the property of all the snapshots that can be reproduced with the same thermodynamical properties. So you want to fix really the temperature and the volume of your simulation, and then sample a few different configurations of your system, and repeat the DFT calculation for each of these different configurations. So it's not just a question that if I have 1,000 water molecules in my system, I have to do a very expensive DFT calculation. The problem is that I have to repeat that a reasonable number of times in order to keep track of the statistical averaging needed to compute a simulation with the liquid involved. And so, I mean, it's still feasible in sometimes, but these are like really like frontier works done with codes which are maybe very highly parallelized. So there are some works by, for example, the group of Michiel Sprick using a CP2K code, which, I mean, he likes to perform fully atomistic QM simulations, and he's good at that, but I mean, it's something that you can't really perform for very different systems, many different setups, so it's not high throughput in nature. And then one may wonder, is the result of this kind of simulation correct? So is really the structure of DFT water, for example, the right experimental structure of liquid water? And the problem is that this is not the case, usually. Because, first of all, DFT water is not exact water, because we don't have the exact DFT functional. So, for example, let's say you use PBE, then it turns out that the melting temperature of water with PBE is off by 50 degrees from the experimental one. And so maybe you are simulating your water at 300 Kelvin, you expect the water to be liquid, and in fact is more solid-like. And then the results clearly, I mean, how can they be correct if water has a different structure than the experimental one? So I don't want to claim that multi-scale approaches are better intrinsically than full atomistic QM calculations, but it's clear that full atomistic QM calculations have some limitations, especially when you have to include so many different aspects in your simulation and you have a liquid involved. So what is one of the solutions, and what is the solution that I propose you and I encourage you to try and play with, is what are called hierarchical models. So the idea is that, especially in a system where, like the electrochemical system that I showed, you clearly have a part of your system which is important, which is where the electrochemical reaction occurs. And then you have instead part of your system which is somehow important because you really want to include its effects, but it's not where the physics is really happening. So the electrochemical reaction is happening on the surface, involves the catalytic species, but the solvent is there to contribute dielectric screening, to help maybe formating or breaking some bonds. But I mean, what are doing the water molecules here that helps the catalytic activity on the surface? What is really the contribution of these water molecules? Why do I need to spend exactly the same effort to describe this water molecule here as I need to describe the atoms in this region of the cell? So I can apply this reasoning to simplify my simulation and focus and treat with the quantum mechanical accuracy only the part of the system which I deem important. There is some arbitrariness in this, clearly, but sometimes it's quite clear what is important and what is not. So, and then I use some fast, maybe approximate model to handle the rest. And I will refer to the rest in general as with the name of environment. This is quite common in physics and chemistry. Everything that is not what you are looking at is the environment. And you can use still an atomistic description of the environment, maybe using classical potentials, and this is what is called QMMM approach. You can use a coarse-grained description, which means you just collect together some atoms and you form some blobs, and then you have a blob description of the environment. Or you can have a continuum, so you can assume that your environment is like a uniform, homogeneous body that surrounds your quantum mechanical system. And this is, for example, a picture of the FMO protein, which is a light harvesting protein with some chlorophyll, which are the pigments that do the light harvesting process. And the pigments are treated quantum mechanically because maybe you want to study the excitation energies of the pigments, and then you need electrons to study the excitation energies. But the protein matrix, you don't really need a quantum mechanical description of that, so maybe you treat that with a classical atomistic force field. And then this protein was actually interacting with some nanoplasmonic particles, which are metal nanoparticles, which in this kind of simulation were treated using a continuum approach. So the importance of this kind of hierarchical models is also quite well expressed in this short paragraph, where they say that I mean, the goal is to evaluate the variation of the energy of the real system in an accurate and efficient way for systems where relatively large geometry changes or changes in electronic configuration in a smaller part of the studied system is strongly coupled to a surrounding that is only weakly perturbed. So you have a part which is which you really need electronic calculations, and it's the important part. And then but this is surrounded by something which is weakly perturbed by this changes in the electronic part. And one way to address this problem is to develop computer codes based on the Schrödinger equation. They make it possible to handle a system of the size that is required. The Carr-Parinel approach is the leading strategy along this line, but it's still too demanding with respect to computer resources to be able to handle the large system necessary, for example, for biomolecular modeling, but also for materials modeling, for electrochemical, for surface science modeling, or extended supramolecular system with the required accuracy. The solution to the problem is instead to combine classical modeling along the lines suggested by many people, and this is the statement of the Nobel Prize in Chemistry of 2013, which was awarded to Karplus, Levitt, and Warshall for the development of multi-scale models for complex chemical systems. So it's a bit of a pity that in the statement they clearly say that the way to go would be the Carr-Parinel approach, and then they don't give the Nobel Prize to Carr-Parinello, but still it's important to stress that the problem. So actually it's a way to push my point of view to you that maybe would just perform Carr-Parinello or Born-Oppenheimer MD. Sometimes the Nobel Prize goes to the people that are cheating and are using more, let's say, fast and some sort of tricks to overcome the cost of these very accurate and very elegant calculations. So let's look at the specific class of models, which is the one that we contributed developing and is the one that you can use with the Environ plugin. So I will speak about continuum models, and in particular, I will speak about the use of continuum models to handle solvation, so to handle the presence of a liquid environment around your quantum mechanical system. So the idea here is, in a continuum solvation model, is that you simply get rid of all the degrees of freedom of the solvent molecules, and you do it by somehow integrating them out. So the idea is you have a liquid, you have to sample different liquid configurations. On average, if I have a solute and I have a liquid around, on average, along a dynamic, the solute will be homogeneously everywhere around my solute. So I can simply assume that on average, I don't have to interact, my solute doesn't have to interact with every single solvent molecule explicitly, but it just has to interact with something which is homogeneous and lies all around my system of interest. And this has a clear advantage that you reduce the number of molecules and you get rid of the need to perform the statistical sampling. So you don't have to run an MD simulation of the liquid to sample off the configurations of the liquid, because this is intrinsically present in the assumption that the thing is a continuum. So by approximating the liquid configurations with the continuum, you are intrinsically taking into account the statistical sampling of the liquid configurations. Yes?
So did you have the interaction between the liquid and the animal solid first? Or you really need
Yeah, so that's a very good question, and it regards the second part. So the idea is you have integrated out everything, but you still need to, integrate these degrees of freedom over the interaction potential between the liquid and the environment, the solute and the environment. So how do you do that? You need to perform this integration. In general, what you do is to simplify the interaction between the solute and the liquid, and only consider like some forms of interactions. The main one, which is usually used in continuum models, is the electrostatic interaction. So one of the reasons the solvent is important in many cases is because it provides some sort of dielectric screening to the electrostatic of your quantum mechanical system. So the solvent molecules will rotate and rearrange, and in general, they will not do it completely randomly, but they will do it so as to minimize the total electrostatic energy of your system, and this means that usually they will orient their dipole moments so as to counterbalance the dipole moment, for example, of your solute. This is the typical dielectric screening. Usually if you have like a dipole solvated in water, water molecules will orient their dipoles so as to almost cancel the dipole of your quantum mechanical system. So usually you have, this is called dielectric screening. So if you have a point charge in a water solution, water molecules will point their dipoles towards this point charge, so as that eventually, if you are very far away from this point charge, you will see a charge which is actually a fraction of the original charge. And this effect can be very effectively described in terms of the dielectric constant of the liquid. So the dielectric constant is really related to this electrostatic screening of your liquid system. So it's important to really understand these two assumptions behind, or these two, let's say, approximations that are at the core of continuum models of solvation. So the idea is that because these are the main advantages, but also represent its possible weaknesses, in the sense that the fact that you get rid of all the degrees of freedom of the solute, it's possible because you really are thinking that the water molecules are everywhere on average. But what happens is that sometimes water molecules are not everywhere on average. Sometimes if you have a stronger bond with the solute, maybe a hydrogen bond water molecule will attach in a preferable site close, for example, to a residue that can accept or donate a hydrogen bond. So that water molecule will not fly all around the solute, and then a continuum approximation may break down because clearly this water molecule is no longer a liquid water molecule, but is a more structural water molecule. And similarly, I mean, sometimes electrostatic is the main, is the crucial factor to describe the effect of the solvent, but sometimes there are other effects due to the solvent. Maybe you have other form of interactions. I mean, electrostatic is usually a long-range interaction, but maybe you have more short-range interaction. Maybe you have some dispersion interaction between the solvent molecules and the solute, repulsion, polyrepulsion, or maybe you have hydrogen bonds. So clearly, only focusing on electrostatic may be a poor approximation in some specific applications. So there are continuum models which go beyond electrostatics. So the two main ingredients of a continuum model are represented by the cavity and the kind of interaction that you want to include. The cavity is basically where you put the boundaries between what is quantum mechanical and what is the environment. So the cavity may be just the region of space around your quantum mechanical system, or may also include some of the structural water molecules if you want to have a more accurate calculation. But there are different ways of defining what is the cavity, because you can, I mean, it's a bit arbitrary saying, I mean, here is the quantum mechanical system, and from here on, it starts the environment. So how do you do that? You can have a spherical cavity, for example, and say what is inside the sphere is quantum mechanical, then the continuum is all outside the sphere. But clearly, if you have, let's say, a very elongated solute, a sphere would not be a right cavity. So usually how people build these cavities is, I mean, the most common model is to, I mean, as the same shape of the molecule or the quantum mechanical system that you want to model. You can build it, for example, using van der Waals spheres centered on atomic positions. This is one possibility. There are different possibilities, and then this cavity can be also sharp, so you can have a sharp interface between vacuum inside the cavity and the continuum outside the cavity, or it can be smooth, so it can go like smoothly from one to the other. It can be rigid in the sense that it's fixed and it doesn't really depend on the interaction between the environment and the solute, or it can be soft in the sense it can somehow adapt. I mean, if you have a stronger interaction between the solute and the solvent, maybe the cavity will get closer to the solute. It can adapt its shape depending on the intensity of the interaction between the solute and the solvent. And as I said before, the main interaction, which is usually always present in the continuum models of solvation, is the electrostatic one. But you can have other terms related, for example, to dispersion and repulsion, or related, for example, to the energy that you need to spend to form a cavity inside your continuum. So usually, I mean, if you want to place your quantum mechanical system in a hole inside a liquid, you need to spend some energy to generate this, to build this hole inside the liquid. This is called usually cavitation energy, and is somehow related to the size and shape of this hole that you need to build. So the most famous continuum model of solvation is the polarizable continuum model, which was developed by Tomasi and co-workers. There are two very extensive chemical reviews on the topic. This is the most recent one, and this is probably the most, I mean, this is quite instructive, but it's a bit old. And it's the method of choice if you do a quantum chemical calculation. In this case, the cavity in this, let's say, vanilla flavor of PCM, the cavity is built as spheres centered on atoms. So it depends on the atomic positions. And is a rigid cavity. So inside the sphere you have vacuum. Outside the sphere you have your continuum, which may be just a polarizable dielectric or may also include other effects. PCM also has formulas to include dispersion, repulsion, and cavitation interactions, which are a bit more approximate and less tuned than the electrostatic one. So what happens when you have this kind of cavity? You have a quantum mechanical system inside the cavity, and then you have this dielectric around. What happens is that the charge density of the solute will polarize the continuum dielectric. So we'll generate a polarization charge, and this is just like simple electrostatic, like basic physics course on electrostatics. The charge, so this polarization effect can be well described by a polarization charge density which is only spread at the interface between these two dielectrics, so between the vacuum and the dielectric. So all the effect of the continuum can be described by a charge density which is spread on this sharp interface. And the nice thing is that this polarization charge is linearly related to the electrostatic potential of the quantum mechanical charge density. And this operator that links the two does not depend on the quantum mechanical degrees of freedom. It only depends on the shape of the cavity and on the dielectric constants of the environment and of the inside of the cavity. So so this operator is just a classical electrostatic operator that depends on the electrostatic setup of your system. So the shape of the cavity, the dielectric constant inside the cavity, the electric constant outside the cavity. So it's something that you can compute, for example, at the beginning of your quantum mechanical simulation, invert once, and then every time you have a new value for the quantum mechanical charge density, you can compute the corresponding polarization charge. Then what you can do is to compute, for example, the electrostatic potential associated to this polarization charge and add this external potential to the Hamiltonian of your quantum mechanical system. So in this way, your quantum mechanical system, so the electronic density of your system, will be optimized in the presence of a polarization charge, which is itself a function of the charge density of the system. So this is to say that eventually polarization charge and electronic density will be consistent to each other, and you have something where the polarization and the electronic density have been optimized together. As you can understand, the calculation of this term is very fast because it only requires to diagonalize this operator once, and then you have only a matrix vector product. So you can compute this potential quite easily. And so the overall cost of performing a quantum mechanical simulation with this dielectric embedding is not very different from a calculation performed in vacuum. So for this is, goes back to one of the motivations that I told you at the beginning. You want something that allows you to perform a simulation taking into account the complexity of the environment, but at the cost which allows you to perform high throughput simulations. And this is, I mean, one of the way to do it, in a sense. You have something that costs as much as doing a simulation in vacuum, but you can take into account dielectric screening effects coming from a liquid system without having to sample and to consider the degrees of freedom of the liquid. PCM is usually solved using a boundary element method approach, which means that you have a sharp interface, so you build explicitly this sharp interface, and then you discretize this sharp interface, and then you solve the electrostatic problem on the surface. So you have a two-dimensional problem to be solved at the boundary between the vacuum and the dielectric or the continuum. It's fast, is very well tested because, I mean, the first review is from '94, and in the meantime, there have been thousands of applications of these models. They are quite the standard in quantum chemistry simulations. So if you want to simulate something in solution, usually you use this kind of continuum approaches. There is, I mean, the problem is that I mean, quantum chemistry codes are not usually thought for example, molecular dynamic simulation. So usually you don't perform MD, you don't have plane waves. So they're not. So the PCM also has some issues when you want to perform, for example, MD simulations, because there are possible problems with the forces due to the fact that the cavity is defined on atomic positions and it's quite sharp. So it's a bit difficult to have a clean definition of forces, and then you have this numerical procedure to discretize the surface, so it's a bit of a mess. And then you have some sort of arbitrariness in the definition of the cavity, in the sense that, in principle, you can define the size of these atomic spheres in different ways. There are some tuning parameters, and in the models, the PCM flavors that work best have a bit of a strange definition of these spheres, in the sense that, for example, carbon atom with 2 hydrogen has a sphere, carbon atom with 3 hydrogens attached have a larger sphere that include all the hydrogens. It's a bit of I mean, physicists usually don't like this kind of arbitrariness in their simulation. And then it doesn't account for the fact for the softness, as I said. It doesn't account for the cavity to adapt its shape when you have a stronger or weaker interaction. I mean, this is, as I said, the work of Tomasi and Menucci is probably the prototype. I mean, it's the most general approach on continuum solvation in quantum chemistry. There are other works by, like, the Cosmo model is still a sort of a sub-flavor of PCM. There are models of PCM in which the cavity is built in terms of the electronic density. There are models which are very accurate in reproducing experimental results, but which involve a lot of tunable parameters. And these models have been implemented in basically all the quantum chemistry codes that you can find around, especially in Gaussian. It's very easy to set up a PCM calculation. Then in 2002, like, 2 physicists / mathematicians developed a model which is, I mean, in its basic assumptions, very similar to PCM, but has some nicer features. And the idea is that basically you can define the total, you basically have a smooth cavity which is defined on electronic density instead of being defined on atomic positions. So the idea is that basically the environment is everywhere there are no electrons. So in your quantum mechanical system, when the electronic density goes down, then it starts the environment. So you can have a dielectric function that goes to, for example, the dielectric constant of bulk water when the electronic density is low, and then goes to 1 when the electronic density is high. In this way, you really have very few parameters, like maybe 1 or 2 parameters, and they control and then determine exactly the shape of the cavity. So it's something which is more intuitive. Moreover, I mean, this cavity will readjust itself along the SCF, because as the electronic density converges, the cavity will also converge to a more defined shape. And the cavity itself will depend on this optimization procedure, so it's soft in itself. You have to, in order to solve the electrostatic problem for this free energy functional, you can do the variational, use the variational principle with respect to the total electrostatic potential, and you come up with this equation, which is similar to the Poisson equation, which would give you the electrostatic potential for the system in vacuum, but for the presence of this dielectric function here, which is now a function of space, because this dielectric function will be different at every point in space. So you actually need to solve what is called a modified Poisson equation, in which you have this space-dependent dielectric function. But once you are able to solve this electrostatic problem, then you can simply add to your Con-Sham potential the two additional terms that come from the presence of this, you can do the variational derivative of this free energy function with respect to electronic density, and you would get the standard R3 potential plus two additional terms, one related to the electrostatic potential coming from the polarization charge, and one related to the fact that the dielectric depends itself on the electronic density. So there will be a term which is the functional derivative of epsilon with respect to the electronic density. The advantage of this approach is that it's fully variational, so this is usually something that physicists like a lot, and the cavity is self-consistent, so it's smooth, so it's a soft, self-consistent cavity. The problem is that the electrostatic problem that you have to solve is no longer a 2D problem, which is just a simple electrostatic, but is a problem which is defined on the whole three-dimensional space. And moreover, you have to solve this problem at every SCF step, because at every SCF step, this electric function will be different. So you are making your life a bit harder. So their idea was to solve this problem using multigrid, which is a faster technique, which allows you to be quite fast in solving this problem. And as this approach has several advantages, but it's clearly more computationally expensive than the PCM. And it can have some convergence problems depending on how you choose the dielectric function. So it's like somehow the exchange and correlation functional. So you have this magic object that contains all the hard part of the problems, but then it's crucial how you define this object if you want to have accurate calculations. And then they really didn't go much in parameterizing and testing the model. And it was just a purely electrostatic model, so it was not including the non-electrostatic terms that were actually instead present in the PCM calculation. And there are many people that started working after this initial work on the Fatehberg-NGG model, and now there is a bit of a rush in different codes to develop more advanced and more accurate continuum models of solvation. And these kind of models are now featured in Quantum Espresso, in VASP, in Big DFT, in CP2K, in OneTap. So basically all the condensed matter simulation programs are investing some efforts in including these kind of approaches in their packages. So let's have a look at what we did in this field, which is basically a redefinition of the Fatehberg-NGG model, in which we added some non-electrostatic terms based on the surface, quantum surface and quantum volume of the system. We changed a bit the numerical approach, and we did quite intensive work on parameterizing and testing the accuracy of the model on neutral and charged compounds. So, as I said, in the Fatehberg-NGG model, what you need to solve is the modified Poisson equation, in which you have this annoying term that forbids you to just do nabla phi tot, so Laplacian of the potential equal minus 4 pi density of the solute. If it were just the Laplacian, you could solve this using FFTs, and it's very efficient and very fast. But since you have this extra term, you need to do something more complicated. So either you use the multigrid as in the Fatehberg-NGG model. The multigrid takes into account everything and solves it. It's a black box, basically. Or exploiting the knowledge of the PCM model, you can introduce in your system the polarization charge, which is basically just a way to move the term that depends on epsilon on the right-hand side. So if you use this definition, you end up with an equation that looks like this. And this is a standard Poisson equation in vacuum. So it looks like you can just solve everything with the fast Fourier transforms. But clearly, the problem is that the polarization charge density is a function of the solution itself. So you can't, so you're just hiding the dirt under the rug, which is the polarization charge density. But then you can iterate this procedure. So you compute the total potential using FFTs, and then you update the polarization charge and go on and on in this scheme. And you solve for the polarization charge in an iterative way. As a matter of fact, you can reshuffle this equation and express the polarization charge in this expression. So as the sum of two contributions, one is just a rescaling of the solute charge density to take into account of the part of the solute charge density that is inside the dielectric. So since we have a smooth dielectric that goes from one to the environment, there will be some part of the quantum mechanical charge density which leak in the environment. And this term here takes into account this leaking, the fact that if I have some electronic density in a region of space where I have the electric different from one, the electrostatic interaction of this leaking density will be rescaled by the dielectric constant. While instead, this part over here is the one which is more interesting and which needs to be solved iteratively in terms of the electrostatic potential. So I can call it iterative polarization charge, and I can solve it using a cycle which basically transforms the total charge density in reciprocal space, compute the gradient of the potential in reciprocal space, and then transforms back the gradient of the potential using FFTs into real space. So I need 4 FFTs to do one cycle on the iterative polarization charge density. It's very easy to implement because it only requires fast Fourier transforms, which are already available in every condensed matter simulation program. And it's naturally parallel because usually this FFT machinery is all parallelized. And it can easily handle periodic system and partially periodic systems, surfaces, and periodicities. So this is what this polarization charge density usually look like. So as you would expect, if I have a water molecule which has like a sort of a dipole in one direction, I will have a polarization which counterbalance the dipole of my solute. This is a simple iterative solver for the polarization charge. In the recent years, we developed even better solvers. In particular, the solution that I just showed is equivalent, can be shown to be equivalent to a preconditioned steepest descent algorithm on the potential, while one can have a more efficient conjugate gradient algorithm, and we can have also smarter preconditioners. So if you are into this kind of numerical problems, I suggest you to read these recent papers, which contains some more information about being even faster in solving this polarization calculation. But the crucial ingredient, as I said, is how you define the function which connects the electronic density to the continuum. So how do you define the epsilon of the electronic density? And so you have some requirements. So you really want this function to be flat where you have an homogeneous environment. Because if you look at the polarization charge density, so this depends on the gradient of the logarithm of epsilon times the gradient of the potential. So if the epsilon is flat, then this polarization is 0. So you really want to have no polarization inside the quantum mechanical system, because that would mean that you have some charge which is maybe very close to the nuclei or on top of the electrons, and this is unphysical. And you really don't want to have polarization charge in the bulk of the solvent because, I mean, it's not physical either in the sense that there should not be fluctuations very far from the solute. And so it needs to be, so in order to be flat where the environment is homogeneous, we defined it as a piecewise function. So we have two thresholds, a rho max and a rho min, and the function is 1, so it's vacuum when the electronic density is higher than rho max, and is the bulk value of the solvent when the electronic density is lower than rho min. And in between, how you define the switching from 1 to epsilon 0. So this should be smooth because you want to be able to describe the polarization charge density with the same grid that you use to describe the other physical quantities in your system, like the electronic density or the, so you want basically this density here to be smooth, so you want this function here to be as smooth as possible. This is a gradient of a logarithm of the dielectric function. So what you want is the gradient of the logarithm of this thing to be smooth. And you want it to be smooth when this function, so this function is defined at the borders of the quantum mechanical solute. So at the borders of the quantum mechanical solute, the electronic density, you know how it decays. It decays exponentially. And it's a well-known result from quantum mechanics. So if you have electronic density and you are like the outskirts of your quantum mechanical system, the electronic density decays exponentially. So in order for the final object to be smooth, you want it to define on the logarithm of the electronic density to cancel the fact that it decays exponentially. And then you want the gradient of this function, of the logarithm of this function to be smooth, and so you need to define it so that basically as the exponential of a smooth function of the logarithm of the electronic density. It's a bit of a tricky part, but this is what makes the final algorithm converge in a stable and robust way. And this is what was missing in the original formulation of Fatehberg and Gigi. Yes?
So here you are meaning that when you are, like, when the electronic density of your molecule is lower than a certain threshold value, you are considering the dielectric constant to be the bulk value.
Yes.
Okay, but this is true only if your molecules are like in a bulk. They have a bulk environment around them.
Yes. So you are placing this continuum dielectric all around this your quantum mechanical system.
Okay.
So let me clarify. So this is the idea of the, it's this idea here. So you have, let's say, a quantum mechanical system with this electronic density, and you want to place all outside of this molecule a continuum environment. So what you do is you say, when the electronic density of this system is low, the environment starts. So let's say this is the electronic density. When the electronic density goes below 0.001, it starts the dielectric. And this will place the dielectric all outside of your system. So it's the nice way, the nice idea of Fatehberg and Gigi of defining what is the cavity. So the cavity is, as I said before, the boundary between your system and the environment. And the idea is that this boundary can be defined in terms of the electronic density. So in a sense, you take an isodensity of your electronic density and say, within this isodensity is the quantum mechanical system, outside is the environment. Then it's something smooth, because you want a smooth definition, because with this definition, the nice thing is that clearly, first of all, you have the interatomic forces, which are much cleaner, because the dielectric does not depend anymore on the atomic positions, but only depends on the electronic density. And then for the Hellman-Feynman theorem, there is not an explicit contribution to the interatomic forces, because there is no dependence of epsilon on the atomic positions. It only depends on the electronic density. And then it's smooth. It also helps in keeping forces and accuracy in MD simulations under control. So it has several advantages. Let's go back to this definition. So this is sort of a key point. So it's important to have a physically meaningful definition of the dielectric constant. So in this definition, we take into account the fact that the electronic density decays exponentially, and that you need to have something which is smooth. So the exponential, which, I mean, if you take the gradient of the logarithm of this something, the resulting quantity is smooth. And then we add, on top of the dielectric model, we add non-electrostatic terms. And so we say that the dispersion, repulsion, and cavitation terms are somehow proportional to the surface and volume of the quantum mechanical system. And this is clearly a bit of an approximation, but in a sense, it's also, I mean, it can be made to work in the sense that cavitation energy is, as I said before, is the energy that you require to spend to build a hole inside the liquid. And this is usually, I mean, for macroscopic systems, is usually considered to be proportional, for example, to the surface tension times the surface of the hole, of the bubble. So if you take a microscopic analogous of this macroscopic picture, you can also say that the cavitation energy is somehow proportional to the surface of the quantum mechanical system. And similarly, you can also say that other non-electrostatic interaction between the electrons of the solute and the solvent may be also proportional to the volume occupied by the electronic density of the solute. Both the surface and the volume can be defined also in terms of the electronic density of the solute. So they can be related to these isodensities of the solute. So also in this case, surface and volume are sort of embedding contributions which are related to the shape or size of the cavity. So is in parallel. So we already have a cavity which we built for the dielectric contributions. We can use the same cavity also to compute the surface and the volume of our quantum mechanical system in a self-consistent way, because this depends explicitly on the electronic density, so there will be Kohn-Sham functionals coming out of these two terms. And everything is defined just in terms of the surface of the electronic density of the solute. So eventually we will have a free energy, which will be the collection of the electrostatic free energy, which I showed you before, which depends on the bulk dielectric constant and on the thresholds that you defined to define the cavity, plus the surface and volume terms, which in our model, so this is our continuum solvation model, which takes into account electrostatic and non-electrostatic. We insert some parameters here, which are then tunable parameters. I used to tune our model to reproduce experimental data. In total, I mean, since we have this definition, which is a global definition, which only depends on the electronic density, we have a very limited number of parameters, because we only have two parameters that control where the cavity is, so how far from the nuclei this environment starts. And then we have these two parameters, which are tunable parameters to reproduce the solvation energies. And then we have some physical parameters, which, for example, are the bulk dielectric constant, experimental dielectric constant of the liquid, and the surface tension of the liquid. So in total, our self-consistent continuum solvation model has 4 tunable parameters. And how do we parameterize them? So how does it perform, especially when we compare, for example, to state-of-the-art continuum solvation models? And here we can see, for example, the comparison just for the electrostatic part between the SCCS and, for example, the PCM as implemented in Gaussian, in the old Gaussian version of G03. So the tuning, so the errors are computed on a set of 13 molecules, and then we repeat the calculation of a set of 240 molecules. These are small organic molecules solvated in water. So you can see that our model gives results in very good agreement with the PCM model when it's optimally tuned. Also with the new version of the PCM, the one implemented in the G09 package. And the same is true also for the calculation of the cavitation energy. So if we compare our calculation of cavitation energies with the one of Gaussian, we also get a very good agreement when we select the optimal set of parameters. But then, so let's say that we optimize the two of the parameters, in particular the two parameters that control the cavity shape, so ρ max and ρ min. We select them to reproduce the electrostatic energies. So using this graph to reproduce the electrostatic energies of PCM. And then we can tune the other two parameters to reproduce experimental free energies of solvation for these small molecules. And these are the results. Clearly, there is a bit more scatter in the results. You can see that if you parameterize with respect to the surface and volume for these small molecules, you can have basically a linear dependence between these two parameters. So basically, they're not independent parameters. You could just use one of the two, maybe just the surface or just the volume. And this is because basically the surface and the volume of these small molecules are very strongly related. Yes. Yes.
So when we are talking about surface, when we are talking about atoms,
yes.
I think this parameter was 0.001.
Yeah. Yes. So. So I mean, this is a good question. In the sense, yes, because these parameters, okay, they are not tuned to reproduce how close the solvent comes to a, let's say, transition metal atom. They are tuned to reproduce how close the atom comes to the atoms involved in this training set, which maybe are like standard atoms of chemical molecules plus halogens plus a few other atoms. But apart from that, we have such a big sample of different molecules and different configurations that we are quite confident that the shape of the cavity that you obtain from these parameters is reasonable enough if you transfer from like isolated molecules to surfaces or more complex systems. The question may be if these parameters can be transferred from one solvent to the other, because these parameters have been fit for water. But in principle, maybe you want to use them to study other solvents with different dielectric constants. If it were not, I mean, the easiest way would be you just change the dielectric constant and keep this parameter fixed, and then you can simulate whatever solvent you like. You just need to have the experimental dielectric constant of the solvent, and then you can go from water to another one. But it's not guaranteed that the parameters that you fitted for water can be used for other solvents. So you can do it, but it would be better if you have some sort of benchmarking when you do it.
If we want to study different systems, is there a way like to calculate the parameter ab initio or to train
Yeah.
them?
So the good point of this model is that only requires two parameters. And so if you want to study a different solvent, you need to have, you can do the same training that we did. You take the solvation free energies of a few molecules on the solvent that you are interested in, and then you change these two parameters so as to adjust to this, so as to minimize the error on the computed solvation free energies. So what you need, I mean, in this parameterization and in the parameterization of continuum models, usually you exploit solvation free energies, which are well-characterized experimental quantities. You can also use different, I mean, if you have access to different experimental data, you can also use different data in the sense that which are related to solvation free energies. For example, one possibility for condensed matter simulations or surfaces would be to use, for example, angle of contact measurements, which are also related to the interfacial free energies of the surface with the solvent. Okay, so if you look at this data, you end up with an average error. So if you take the best performing set of parameters, you have an average error which is 1.2 kilocalorie per mole. I apologize for the units which are more typical of chemists. But what we, as a chemist, would consider accurate or chemical accuracy is defined to be 1 kilocalorie per mole. So if your calculation allows you to be more accurate than 1 kilocalorie per mole, then you say that you are chemically accurate. We are a bit above this, but not too far. And the best performing quantum chemistry continuum solvation models can go to 0.5 kilocalorie per mole, but here we only have 4 tunable parameters. In their models, they maybe have some tens of parameters, so 20, 30 parameters. So it's a bit, so this is clearly easier to tune and to set up if you want to do a different system, a different solvent, because you only have to tune 4 parameters. And I mean, we are working on improving on the accuracy of this. And the other good point is that actually, if you look at the errors and you break down the errors in terms of the different functional groups that are present in the molecules that you considered, you can really see that the largest errors, the red boxes, are associated with molecules, amines, acids, ethers, which form very strong hydrogen bonds with water molecules. And so actually, as I said at the beginning, you really, I mean, you don't want your continuum model to perform well on these molecules because the continuum approximation breaks down for these molecules. So it's actually a good feature, the fact that our model gives poor results on these molecules. And now we have a clear way to improve on these results, which is to include explicit water molecules in our simulation set, in our simulations, to take into account the fact that some of the water molecules are not homogeneously distributed, but they are specifically placed in specific bonds so they are structural water molecules. They are not liquid-like water molecules. You can do molecular dynamic simulations. This is a Born-Oppenheimer MD done with PW, and energy is conserved as well as in vacuum if you are careful with the numerical parameters. You can study charged systems. So charged systems pose some problems in terms of simulations because periodic boundary conditions give artifacts in charged systems, and you have if you want to study an anion with plane waves, you may have that DFT just go nuts because basically DFT doesn't bound the extra electron. And in quantum chemistry simulations, you don't see it because basically you have a localized basis set and the electron is forced to stay on the atoms. But in plane waves, basically the electron, if he wants, he can jump and be like a continuum free electron, and then the SCF will just go nuts. And then there is a problem that if we have problems with let's say acids and amines which form strong hydrogen bonds with the water, the problem is even stronger when you have an ion, because this is clearly forms strong bonds with solvent molecules. So I will skip the part on PBC because PBC corrections, because the theory is a bit lengthy. But the problem is that basically in all the procedures that I presented, we exploit FFTs to compute potentials given the charge densities. But FFTs intrinsically assume that your system is fully periodic. If you want to have a continuum solvent, your system very likely is at least in one direction, not periodic. So if you have a surface, you have at least one direction, and the solvent above, you have one direction in which the system is not periodic. If you have an isolated molecule, you have 3 directions in which the system is not periodic. Usually when you have a continuum environment, you need to have some aperiodicity somewhere. And so you need to introduce periodic boundary corrections. And these corrections are actually already present in Quantum Espresso. There are some. But you need to take into account the fact that you have also a continuum dielectric. So these corrections need to be upgraded for the presence of this dielectric in the system. And this has been done in this work in 2014. So there are different strategies, and they're all implemented in the Environ module. And this is particularly crucial if you want to study, for example, a slab with a dielectric solvent on top, because the problem is that if you have a dipole along the direction of the slab, this will generate a finite electric field, a finite it will generate a jump in the potential in your system. But since you have periodic boundary conditions, the jump in the potential cannot fit in periodic boundary conditions, and so you will add up a slope in your potential, so a finite electric field to compensate for this shift in the potential. And this gives artifacts when then you compute polarization charge. Because if you have a slope in the potential, then you have a spurious polarization charge coming from this PBC artifact. And so you really need to take into account the PBC corrections if you want to do a solvation calculation in this setup.
And what happens to have like charge ion over the surface?
Yeah.
One thing is also is alpha and beta parameter because it has been also figured for
Ions.
Molecules.
Yes.
But those are working also in the surface. And I have a surface.
Yes. So in principle, yeah, it's the same question as before. I mean, ideally, you would need to benchmark your data and be sure that everything is consistent. But ideally, the values of alpha, beta, rho max, and rho min that you parameterized for neutrals or for charged species should be transferable if you consider like a surface setup. Because, I mean, they really depend on the electronic density, on the quantum mechanical properties of the system, not on the geometrical arrangement of the system. Clearly, I mean, there may be problem if you have different atomic species and maybe they are not, I mean, it may be more a problem of the kind of elements that you involve in your calculation rather than the fact that you have a surface or an isolated system. Anyway, this is to show what happens when you consider like PBC corrections. For this is our calculations on a charged isolated molecule in a cubic cell. You can have different strategies to remove PBC artifacts. If you don't remove the PBC artifacts, so you have periodic boundary conditions, the energy will go down as 1 over L, where L is the size of the cubic cell. So your energy will never converge. You will need to go to very large unit cells. If you add these corrections, your energy basically is converged for reasonably small cell sizes. In particular, the Martina-Tuckerman gives you correct, converged results. So it's the best performing, let's say, algorithm. But you need to be sure that the size is large enough, because if the size is a bit smaller, then it can give much worse results than the other approaches. The other approaches, basically, the Markov-Payne or the point counter charge, they are quadratic corrections, so they correct for terms up to 1 over L to the cube power. So this is what happens for the same system in solution. So the error is smaller than in vacuum, because in solution, as I said, the monopole moments and dipole moments of the solute are screened by the dielectric. So usually the PBC artifacts are smaller. If you want to compute the solvation free energy, which is the difference between the two, you see the same trend. And this is how the errors go, for example, for the Markov-Payne calculation. So if you compute the different contribution, you see that the residual error, it goes down as L to the minus 5. So as you increase the cell size, you have still an error, but it's as small as L to the minus 5. With the dielectric, you can also find a smart way to overcome the problem of converging anions in vacuum, but I will also skip this because we don't have time. We parameterized the CCS also for ions. So it turns out that cations actually come out pretty well already with the standard parameterization, while anions are a bit more tricky, so you need the specific parameterization to study negatively charged systems. And so, as I said, everything has been implemented in the Environ module. So it's not currently distributed together with Quantum Espresso, but it's still available on QForge. There has been two releases. The last one is compatible with Espresso 6.0 and Espresso, a previous version of Espresso up to 5.1 point something. There is a web page where you can find all the infos about this Environ module. And to run it, you just need to run the executable with the ---- Environ option. There is an independent input file, which is called environ.in. And there are some printouts which are shown in the output. There is an internal verbose keyword, and it's not interfaced with the post-processing, but you can print out some of the physical quantities as cube files, so I'll show you during the tutorial. So Environ is a collection of external interaction potentials. So there is the continuum dielectric, there is the surface term, the pressure term, there is the PBC correction term. So each of these embedding can be used individually. SCCS, so our solvation model, is a collection of these different terms, each term with an intensity which has been tuned, so that if you take them all together, you can reproduce solvation energies of molecules in water. But nothing forbids you to use each of the different external potentials individually and tune them individually and adapt them to the simulation that you want to perform. In particular, there is the continuum dielectric, the external pressure, the surface tension, the PBC correction schemes, and then there is the possibility to define by hand fixed charge distributions, which have the shape of Gaussians, maybe like a sphere-like or wire-like or slab-like Gaussians. So you can have 1D, 0D, 2D charge distributions in your simulation cell. And you can also define from input dielectric regions. So you can define from, I'll show you in the slide. So this is the external charges. You can define dielectric regions, for example, to force, for example, the solvent not to enter a certain region. For example, if you have a nanotube and you want the dielectric continuum to be only on the outside, since the continuum is defined on the electronic density, it would also go inside the tube, but you can force it to stay outside by defining this dielectric region. And you can use dielectric regions also to simulate, for example, interfaces or nanoparticles or other features or like complex dielectric environments in your system. Having said that, these are some references. I know that the time is over, but I will ask you if you can wait 5 minutes because there is a Yuri Timbrov that you may have seen in the previous days that will show you some slides about how to compute optical spectra using these continuum models. So Environ has been interfaced also with TDDFPT program, and you can compute optical spectra of molecules with the continuum environment. And this is actually a very nice feature, and it's very good work from Yuri. So these are the references related to Environ. These are some of the applications of Environ that have appeared already in the literature concerning, for example, the oxygen reduction reaction on platinum, nanoparticles or surfaces, like proteins or other catalysts. And these are the people involved in the project. So as I said, Nicola Marzari, then a group of people from Basel, and then Stefano Baroni and Yuri for the TDDFPT part. And so sorry if I am a bit late, but bear with me 1 second.
Another slide?
There are 3 slides.
3 slides, okay. Let me see which ones. Okay.